Okay, let's unpack this. We're doing a deep dive today into source material that looks at a really fascinating angle on optimization.
Mm.
I mean, when you think about optimizing something, it can feel pretty broad, you know?
Sure, yeah.
But this source really narrows it down. It's about optimizing veterinary drug schedules.
Exactly. And what's really interesting, I think, is how the source links this practical thing to a mathematical concept you probably know, differentiation.
Right?
So our mission, just sticking to what the source gives us, is to figure out how differentiation actually works in this specific situation.
Okay, so let's jump into the source's main idea then. It seems to argue that the way to find the best drug schedule involves using the derivative.
That's it.
That's presented as the sort of fundamental math tool here for getting that optimization done.
Right. And what is it we're actually optimizing? The source is clear. It's the schedule itself.
The timing.
Yeah, the timing, maybe dosage levels too, for giving drugs to livestock. We're trying to find the schedule that gives the best result
Mhm.
based on, whatever criteria the source lays out.
And, okay, here's where it gets interesting. Because the source adds this layer of complexity. It makes a point that this isn't just any livestock.
Oh, all right.
It's specifically for livestock raised near crops treated with pesticides.
Yes. And that environment obviously changes things. It brings in variables that could make a standard drug schedule, well, not work as well, or maybe even cause issues.
So that's where the math comes in, according to the source.
That seems to be the argument. I mean, you probably remember from studying calculus, differentiation helps find maximums, minimums, those points where the rate of change hits zero.
Turning points on a graph.
Exactly. So the source suggests that to optimize this complex drug schedule, you need to model certain things, maybe how the drug concentration changes in the animal over time, or how you balance the drug working effectively against how the animal processes it,
Yeah.
especially with those environmental factors from the pesticides nearby.
Right, those external influences.
So differentiation, by helping pinpoint those key moments, like when does the drug concentration peak, or when does it drop too low, or maybe when are potential interactions most likely. That becomes the way, mathematically, to figure out the optimal timing or maybe the best dose adjustments needed for that specific environment. The source frames differentiation as the practical method to nail down the best schedule by looking at those rates of change.
Wow, okay. So think about that connection for a second. This abstract concept from math class, finding a derivative.
Yeah,
The source presents it as having this really direct hands-on use
totally.
in something as concrete as keeping livestock healthy, specifically when they're in this challenging situation near pesticides. It's
Yeah.
not just theory on a page.
No, it's a tool for a real problem.
Yeah.
And that's what's so fascinating. That bridge the source builds.
Mhm.
It takes a core math concept, differentiation,
Yeah.
and applies it straight to optimizing something really practical and kind of complex.
Figuring out the best drug plan for animals under specific environmental stress.
Exactly. It just shows how powerful these analytical tools can actually be in the real world.
It really does. And it kind of raises a question for you, the listener, as you're learning about concepts like derivatives. What other seemingly abstract math tools might be working behind the scenes, optimizing things in places you'd never really think about?
Yeah,
To
absolutely.
think about all the different real-world challenges, logistics, biology, whatever it is, where finding the best way might just come down to finding a maximum or a minimum or understanding a rate of change.
It makes you think about how deeply connected that sometimes abstract seeming math is with very concrete problems that need solving.